Gibson here. Today we're going to look at what it means to optimize a quadratic function, or sometimes we say optimization of quadratic functions. So let's look at our objectives. First, we're going to get a conceptual understanding of what it means to optimize a quadratic function, and then we'll work through a couple examples. So let's just define in the broadest terms what it means to optimize something, or what does optimization means. So optimization is the verb form. It means the action of making the best or most effective use of a situation or resource. So I'm sure heard or used this word even in our everyday lives, but mathematically, it's the procedure for finding the minimum or maximum of a function that does this. In other words, a function that tells us mathematically how we can make the best or most effective use of a situation or a resource. So let's look at a simple example here to understand this conceptually. It comes from physics, and we have a ball. So what angle should I throw the ball in order for the ball to land at the maximum distance? So this would be horizontal distance along the ground. And the assumption here is that we're going to throw it with the same speed each time, as fast as we can, but that's our limit, right? As fast as we can throw it. So what angle would I throw it at for it to travel the greatest maximum distance? So experimentally, we could throw it, right? Let's throw it first at 30 degrees, right? And we could measure how far the ball traveled along where it hits the ground. Let's do it again for 45 degrees. And let's do it one more time for 60 degrees. Okay, now looking at these three sets of data, we can clearly see that at 45 degrees, the ball would travel the maximum horizontal distance. It actually turns out that for 30 and 60, they have different heights, but they would actually travel the same horizontal distance. So a way to describe our findings in words is to say the optimum angle to throw the ball is 45 degrees to result in the maximum distance. Okay? Or another way to say it is we can optimize the distance by throwing the ball at an angle of 45 degrees. Okay? So in this case, the situation or resource is we can only throw the ball so fast or throw so hard. And what angle should we throw it at then to give us the optimum distance in this case? All right, so we can find the optimum condition or values by experiment, like we just saw by throwing the ball and measuring it, or if we can write a mathematical function, we can find its minimum or maximum. So that's what we're going to work on today, is how can we create a quadratic mathematical function and find its minimum or maximum. So let's just review. I know we've done this in previous lessons, but let's just review how do we find the minimum or maximum of a quadratic function or equation. So let's take an example here. Y equals negative x squared plus 2x plus 5. So first off, are we finding a minimum or a maximum? Well, we need to determine whether it opens up or down. So the -1, our a coefficient, right, tells us that the parabola is going to open downward or have a reflection. So if it opens downward, that means we are going to have a maximum at the vertex, the maximum value of the function. All right, so how do we actually find that maximum value? Well, we're basically finding the coordinates of the vertex. So if you remember, the equation we use to find the x coordinate is -b over 2a, and we plug in our coefficients of a and b. So let's do that. We have a +2 for b, a -1 for a. Don't forget the form itself has a negative out front, so this would simplify to a +1. And then when we're asking for the maximum in this case, it's actually the y value that we need to find. So how do we find the y value? We're going to take the 1, right, and plug it back into our original function. So 1 squared, and then apply the negative, gives us a -1 plus 2 plus 5. That gives us a total of 6. So the vertex, right, would be at the coordinates x equals 1 and y equals 6. And the maximum value is the y value. So we would say this quadratic function has a maximum at y equals 6. Okay, so that's kind of the procedure that once we have the equation, right, we can find the minimum or maximum value, right? Let's look at an example that's a little more real life here. So model rocket, it has an altitude h in meters, and it has time t as its other variable. And we have a function that tells us how high it will fly based on how much time or seconds it's been flying. So that's our equation, h equals 50t minus 5t squared. So we want to find the maximum height of the rocket, and then how long does it take to reach the maximum height? So the height in meters and the time in seconds. Now, this may look a little different than the quadratic equations or functions we've been working with. All we've done is replace y with h and x with t. Also notice that we kind of switched the terms around a little bit. The quadratic term is actually second, minus 5t squared. All right, so good first step is to identify our coefficients. So A, we have a -5 because it's the coefficient for t squared, 50 for the B term, and then we don't have a C term. We'd say that's a 0. All right, so now let's go ahead and find the x coordinate, just like we did in the previous example. Right? We're going to plug it into our formula. In this case, we're calling it t, but it's the same as solving for x. So we put in 50 for B, -5 for A. And if we simplify that, right, we get a negative divided by a negative, which gives us a positive 5 seconds. So that's really the answer for part B, right? How long or how much time does it take to reach the maximum height? Okay, but now we want to find what is the maximum height. So let's put in 5 for x, or t rather, and solve for y, or h in this case. So let's do the math. 5 times 50 is 250 minus 125 gives us 125 meters. Okay, so we know the rocket is going to reach a maximum height of 125 meters after 5 seconds. So in terms of optimization, we could ask the question, how much time do we have to let the rocket fly, right, before it reaches its maximum height? And we could answer it with the minimum and our maximum values we found here. Now, what if we have a problem where we don't have the equation? We have to come up with it ourselves. So let's go through this example. It says, what are the dimensions of the rectangle of greatest area that can be formed with 200 feet of fence? Okay, so good thing on some of these geometry problems is to draw a picture. So here's our rectangle. We're going to call the long side the length, the short side the width. And what do we know from geometry about the area and the perimeter, right? The area is what we are trying to optimize here. It says find the greatest area. So we know the area of a rectangle is length times width. How about the perimeter? Well, we know the perimeter is the length all the way around. So we have 2 lengths plus 2 widths. All right, so our goal here, right, is to come up with an equation that relates these 2 values and more than likely give us a quadratic equation. So let's define the variables here, right? Well, let's let x equal the length, and we'll let y equal the area, right? Because remember, we're trying to optimize the area. So whatever value it is we're trying to optimize, that's what we want to have y stand for. So how do we write a expression for the width if the length is equal to x? Well, what other information were we provided, right? We were told that we have a total of 200 feet of fence. So we know if we use the equation for the perimeter, right, 2 times x, our length, plus 2 times the width has to add up to 200 feet of fence. Now, again, our goal is to have an equation, right, that only has x and y in it. So we have to have an expression that we can have for w. So If we were to solve for W here, right, we're going to subtract 2x from 200 and then divide by 2. And we see that we can write an expression for the width as equal to 100 minus the length, or x. Now, how are we going to use that? Well, let's write our equation now for the area, right? We know the area equals length times width. So the length is x, and the width we just found as an expression using x, 100 minus x. So if we multiply or distribute the x, you'll see we get a quadratic equation, 100x minus x squared. Notice the x squared term we wound up with. That tells us that this is a quadratic equation. So now we need to find the maximum area. And we're going to do that right first by using our equation minus b over 2a. So we put in 100 for b and -1 for a, our coefficients. We simplify that, right? We see that we will get a maximum area if x is equal to 50. In other words, the length is equal to 50. So if the length is equal to 50, what should the width be? Well, we can find that by using the equation we came up with for the width, right? 100 minus x. So if we put that in, we would see it's 50. Now, what did we actually find? It turns out that the rectangle that has the greatest area is actually a square. If we make the length and the width equal to each other, we can get the maximum area for the 200 feet of fencing that we have. Okay, so a square is a special case of a rectangle. So we did find a rectangle, but it turns out that a square will give us the maximum area. Okay, so there's an example of a problem from geometry where we had to write the quadratic equation first, and then once we have that, right, we know how to find the minimum or maximum values that we're trying to optimize. All right, so we know what it means to optimize a quadratic function conceptually, and we worked through an example, a couple examples too, where we had the equation already, and then the third one where we had to come up with our own equation first and then find the minimum or maximum. Okay, that's it for today. Check out Google Classroom for the assignment that goes with this. You've got about 5 or 6 problems to give you a little more practice.